Okay, this is exam 1 for Physics 201, Fall 2011. It says, which of these is the appropriate answer for this mathematical operation? Well, you first want to do the division. That's 3.4 divided by 1.24. If I put that in, I get 2.7419, but the appropriate number of sig figs is just 2 sig figs, so it's 2.7 plus 6.72. And doing the appropriate number of sig figs, the appropriate number of decimal places, which is the lowest number of decimal places, just one decimal place, I get 9.4. So the answer for this is D. Number 1 is D. Which of these equations are dimensionally correct? Okay, you just want to put in the units for each variable. So velocity is meters per second, and that's squared. And then V naught is also meters per second, and then it's squared, so we're okay so far. And then we have 2a. 2 doesn't have any units. A is meters per second squared. And then x minus x naught is just in meters. So I have meters squared per second squared all along, so that one's correct. Then I have xma, that's meters, kilograms, meters per second squared, equals m is kilogram, v is meters per second. So I have kilogram, meter squared per second squared. So far, so good. Minus a squared is going to be meters squared per seconds to the 4th, second squared, and kilograms. But my second squared cancel and leave second squared in the denominator, which is also kilogram meter squared per second squared. So far both of these are okay. And then I have kilogram meter squared per second to the 4th, that's meters per second squared, equals kilograms meters squared per second squared. These do not match up. So it's just 1 and 2, that's D. Estimate the volume of your closed fist in cubic centimeter. If you consider your closed fist to be like a cube, that cube is going to be about 10 centimeters on a side. So 10 by 10 by 10 is 1,000. So the answer for number 3 is C. 10 by 10 by 10 is 1,000. If you consider any other of these options, they are not reasonable. So if instead we went for B, that would be a cube or a rectangle 10 by 10 by 1 centimeter. And that's certainly not your fist. And if you consider this one, it would be 10 by 10 by 100. So that would be like a 1 meter fist that was 10 by 10 centimeters on the other side. So the answer is C. All right. This graph is relevant to the following, just this question actually. What is the position at t equal 20 seconds? All right, well, this is t equal 20 seconds. The position we just read off is 30 meters, so that's A for number 4. The current standard for the kilogram is the metal cylinder in France. Why are scientists seeking to change the standard we use for the kilogram? All right, this kilogram is changing. It's losing mass, as we remember. It's not accessible to everyone, only the French. It's not based on some fundamental constant of nature, and so it's all of these. So number 5 is D. Which of these has never been a standard for a meter? Okay, well the current standard is this. That is the current standard. It used to be the length of a particular bar, so that's not it. And it used to be the distance, a fraction of the distance from the equator to the North Pole. It has never, however, been this value. Remember, the cesium atom is, we base our standard for the second on the frequency of the cesium atom, not the meter. Consider the motionless particle. What is the sign of the acceleration? Well, the velocity is negative and increasing, so that means that the acceleration is negative. Since the velocity is increasing, the acceleration and the velocity are in the same direction, so it's negative. That's A. Number 7 is A. Does the odometer in a car measure distance or displacement? It measures distance. So 8 is B. When throwing a ball straight up, which of the following is true about its velocity and its acceleration at the highest point? At the highest point, it comes to rest. So V is equal to 0, but the acceleration is not 0. It's still minus 9.8. Consider this position versus time graph. The vertical lines mark particular points. At what point is the velocity 0? The velocity is 0 where the slope is 0. That's at this point right here. That's B. Which of these are scalar quantities? Speed is scalar, mass is scalar, displacement and velocity are vectors. So it's 1 and 3. That is C. From the same height and at the same time, one ball is dropped. and another ball is fired horizontally, which one will hit the ground first? All right, if they both hit the same time, it's like if you have a ball here and here, this one you shoot out, and this one just drops, this one falls in the same amount of time, and they hit at the same time. Previous problem, which ball has the greater velocity at the ground level? Well, this one has the greater velocity because when it gets over here, it has a component in that direction and a component in that direction. So the fired ball, B, has the greater velocity. This figure shows two vectors, A and B. What is the resultant vector of B minus A? All right, so draw B first, minus A. This is B, this is minus A, and so the resultant looks like that. That is C. So number 14 is C. Consider the motion of the particle described by this graph. Which of these statements best describes the particle's motion? Does it have negative increasing velocity? Well, this is velocity, and it's in the positive, so no, it's not. Is it constant positive velocity? It's not constant, it's increasing. Is it constant positive acceleration? All right, the slope is positive, so it is positive acceleration, and the slope is constant, so it's also constant. So number 15 is C. Let's just look at D. Is it negative acceleration? No, negative acceleration will look like that. That is a negative slope. All right, let's look at the free response. Derive the equations of motion. All right, we want to start first with our definition for acceleration. Acceleration is equal to dv dt, the first derivative of the velocity. So A is equal to dv dt, and then I can write dv is equal to A dt, and I integrate both sides to get an expression for v, and that's equal to at plus the integration constant, and that integration constant is just the initial condition, which is v naught plus at. So that's our first one. And then the second one is based on the definition of velocity, which is the first derivative of the position function, dx dt. I can rewrite this for an expression for x is equal to v dt. To get x, I integrate. So x is the integral of v naught plus at. That's my expression for v from over here, times dt, or the derivative with respect to t. And so x is equal to v naught t, it's 1/2 at squared, plus my integration constant. So x is x naught, that's my initial condition, plus v naught t, plus 1/2 at squared. So these are my two equations. That's how I derive them. All right, a particle's position is given by this function. I want to first give functions for the particle's velocity and its acceleration. So for part A, the velocity is just the first derivative. That is going to be 3.4i, the derivative with respect to t, plus 5.6 minus 9.8t in the j direction. And then the acceleration is the derivative of this velocity function, which is just going to be minus 9.8 in the j direction. And then for part B, it asks what is the magnitude and the direction of the particle's initial velocity. Well, the initial velocity occurs at t equals 0, and so I just plug t equals 0 into this function. And I get that the velocity at t equals 0, that is the initial velocity, is 3.4i plus 5.6j. That is my initial velocity. And then if I want to find the magnitude and direction of that, the magnitude of v naught from the Pythagorean theorem is 3.4 squared plus 5.6 squared, which gives me 6.6 meters per second. And then I want to find the angle for this vector is the inverse tangent of the y component over the x component. That's 5.6 over 3.4. Let's see, I get 59 degrees. And since my x is in the positive and my y is in the positive, then this angle is measured above the x-axis. So above plus x-axis. So that's the direction. I'll be looking for both of those. The third part is sketch the velocity versus time graphs for both the x and y components of the velocity. All right, the x component of the velocity, that is vx over t. And by the way, I made this is slightly different, but I want to assume, as it says in the next part, that the motion stops when it hits the ground. That is, the motion stops when the position function is equal to 0 in the x and y components. So my velocity in the x direction, this doesn't really affect it because my velocity in the x direction is not dependent upon time. It's just always constant, and so it looks like this. And in fact, it's at a level of 3.4. It's always 3.4 meters per second. Now, the velocity in the y direction, if you haven't guessed it yet, this is a projectile motion. The velocity in the y direction starts out positive. All right, it actually starts out at 5.6, and then it decreases linearly. And then at the top of the trajectory, that velocity goes to 0, and then it keeps increasing, in the negative direction, speeding up in the negative direction until it hits the ground. If I were to plot the path of this, it would look like this. Simple projectile motion problem. Now, let's look at part D. What is the total time the particle is in motion? And again, assume the particle stops when dt is equal to 0I plus 0j. In other words, when it hits the ground. Now, I want to know the total time that it's in motion. I know that at the top, that the velocity is 0. So I can say then that v top is equal to v naught y plus ay t. And that's going to be 0. V naught y is 5.6 plus negative 9.8 times t. And I'm going to call this t1/2 because it's half the total time. And if I solve this for t1/2, I find that half the total time is going to equal negative 5.6 over negative 9.8, which is going to be 0.57 seconds. And then the total time is going to be twice that, which is 1.1 seconds. So that's part D, 1.1 seconds. And then what is the maximum horizontal range of the particle? For E, well, I want to know x. And this is just equal to v naught x times t because there's no acceleration. And v naught x, we've already said, is 3.4. The total time is 1.1 seconds. And that gives me a range of 3.7 meters. So that's number 17. Number 18. I have this graph. I want to know what is the velocity at t equal 35 seconds. Well, this is velocity on the y-axis. At 35 seconds, which is right here, the velocity is 10 meters per second. Just reading it straight off the graph. No calculations. What is the instantaneous acceleration at t equal 5 seconds? That's right here, or right here. I want to find the slope of this line. I do rise over run. The rise goes from negative 20 to 30. So that's 30 minus negative 20 divided by the run, which is 10 minus 0. That's 50 over 10, which is 5 meters per second. So that's the instantaneous acceleration. What is the average acceleration from t equals 0 to 30? That is from this point to this point. I want to know the average acceleration. All right, so it's just Vf minus Vi over my change in time. Vf is 0 minus Vi, which is negative 20. Divided by 30, that's 30 minus 0. So that's 20 over 30, which is 0.67 meters per second squared. And then the final, what is the distance traveled during the particle, during the time interval from 30 to 50 seconds? All right, the distance traveled is equal to the area under the graph. That's the x-axis. I want to know this area, and that'll tell me the distance traveled during that time. And then also this area. So I have a triangle at first, and then a rectangle afterwards. So it's 1/2 base times height for the triangle plus base times height for the rectangle or the square. And so that's 1/2. The base is 30 to 40, so that's 10. The height is 0 to 20, so that's 20. And then the base and height are the same for the rectangle, so that's 10 times 20. So that is 100 plus 200, which is equal to 300 meters. So that's the total distance traveled during 30 to 50 seconds, during that 20-second interval. Now, a car is traveling at 100 miles per hour when a state trooper begins pursuit. The car slows down and comes to a stop in 22 seconds. What is the car's initial speed in meters per second? This is just simple conversion. 100 miles per hour. In 1 hour, there are 3,600 seconds. In 1 mile, there are 1,609 meters. That cancels the miles, cancels the hours, and it gives me 45 meters per second. By the way, that's the number that we had for the, the Nicolas Cage flick. All right, so how far does the car travel after it begins to slow down? How far does it travel after it begins to slow down? Well, I know that t is equal to 22 seconds. I know that my final velocity is equal to 0, and my initial is equal to 45 meters per second. And I want to know what is x equal to, and in the course of that I also need to know what is a. In fact, I first need to find a. So I say v is equal to v0 plus at. I know everything here but a. 0 is equal to 45 plus a times 22. And then solving for a, I get it's negative 45 over 22, which is negative 2 meters per second squared. Now I have the acceleration. It's fairly easy to find x. X is equal to v0 t plus 1/2 at squared. I know all these values. That's 45 times t, which is 22, plus 1/2 negative 2, because he's slowing down, times 22 squared. And that gives me the value, which is 510 meters. So that's how far he travels, 510 meters. That's part B. That's part A. And part C, at t equal 11 seconds, what is the car's speed in miles per hour? So now I know its acceleration. To find its speed is just really plugging in. I say v is equal to v0 plus at. My v0 was 45 meters per second, plus negative 2. That's my acceleration. And t is 11 seconds that was given. So 45 minus 22 is 23 meters per second. And then I want to convert it back into miles per hour. So that's going to be 3,600 over 1,609. And that'll put it back into miles per hour. And that gives me 51 miles per hour. So you see he's roughly at half the speed, but not quite. It's not necessarily, it doesn't really work that way, that at half the time it's half the speed. All right, one more. You drop a rock into a deep well and 3.2 seconds later hear the splash. How far down is the water? You drop a rock. It goes this far. I want to know what is y. I know t is 3.2 seconds. I know that v0 is equal to 0. And I know that the acceleration is negative 9.8 meters per second squared. So how far down is the water? Y is equal to v0 t plus 1/2 at squared. This was just like a homework problem, by the way. That's the v0 goes away, so it's just 1/2 times minus 9.8 times t squared, which is 3.2 squared, which gives me